let's continue where we left off with chickens, and let's use this as more practice for Wednesday. Yes. We were building flocks. Now, it's been about a week. I apologize for the 120 hours between us. But I want to go back to the beginning and rebuild the distributions for the small flocks and then work up to my flock. Because the point is, I want you guys to understand how I was able. This whole lesson started because when we went to buy our chickens, the guy at the store said there's a 90% chance that one of the little birds is a girl. And I'm holding the Happy Meal box with 4 of them in there, and I think there's a 1 in 3 chance I got a rooster in here. And that blew his mind. And it shouldn't have blown his mind from a statistical point of view. And that's what you're going to figure out today, is why it shouldn't have blown his mind. So let's build the flock with just Bertha. Bertha was in rare form this weekend. I started letting them out because the garden shut down now, so they're running all over the backyard chasing the cats around.
Oh, that's fun.
It's just hilarious watching chickens chase cats. 14-year-old cats getting chased by 4-year-old chickens. Geriatric war. So, flock number 1. 1 bird, and 1 bird only. And we've done 1 and 2, correct? So I'm going to kind of recap it.
Yeah.
1 bird. And I say 1 bird, not 1 girl.
Right.
Why?
Because that's what we're figuring out.
We're figuring out how much of that flock is girl and how much of that flock is boy. That's the whole point. This becomes a statistical problem because that bird that is inside that box is not 100% female. On average. On average. It's either female or it's male. But on average, it's a false positive or a false negative, yes? It becomes that question. And that's the problem with math. It doesn't teach you about the maybe. There's a false positive, false negative, just like there's a true positive and true negative. So when they test these chicks in whatever way they do, they say, girl. Okay, maybe you're right, maybe you're wrong. We know that it's right 90% of the time according to this breeder. So, we have number of girls, because as Madeline correctly pointed out, that's what we're interested in. It's, well, at least for us, because we want eggs. And we have the chance of it. And for 1 girl, it's not that interesting, right? Not that interesting with 1 girl, or with 1 bird. Because how many girls could you have in a flock if you buy a bird? You could have 0 or 1. We hope for 1. We might get 0, though. What are the chances? One of my favorite questions in the world. What are the chances of that happening?
90% that it's a girl, which means it's 10%. No.
Beautiful. Because as you guys remember, this column always has to sum to 100%. That is not going to change ever for the next 3 weeks we're together. It can't. That's the definition of a distribution. It can never change. That's the beauty of this. That's the beauty of me forging forward today without worrying about it, because I'm not going to screw you up at all. Because it's still the same thing. The only thing that's going to be a little bit different today versus what you're doing on Wednesday is we're going to be creating these columns today. That's what makes it more fun. We're actually going to be making the P of X column, where on Wednesday I just give it to you. Cool! On average, how many girls do I get? Mu girls.
It's 0.9.
It's 0.9. Ooh. Say that again. I heard the word percent somewhere. It's not 90%, although you can view it as, this is the number of girls. You get 9/10 of a girl per 1 bird. Now, if you say 90% of a bird, I got no problem with that's correct. 90% of a bird is correct. But it's not a probability, it's actually a number, and that'll make a little more sense when we move into 2 and 3 and 4 birds. Does that, 90%, you can say 90% of a bird, that's totally fine. I got no problem with the same. The trick with that is it's going to be harder to say that as the flock gets bigger. And that might be kind of cryptic right now, we'll get into it when we get into 2 and 3 and 4. So I like to think of it as, when you're talking about an average, you're averaging these numbers over here. You're not averaging these. Your data's always in this X column, just like it's always been since week 2. Your data's always been in this column. So the average has to have the same unit as whatever this column is, which is the number of girls. So it's 9/10 of a girl on average. Now, if that upsets you, if you're trying to envision a chick that's 90% female, just realize it means every 10 birds you buy, you're getting 9 girls and a boy on average. They come in clumps, but that's on average what it ends up being. The average is the idea of a long term. If I keep sending Max in to buy 1 girl, and then, or 1 bird, then next year I send him again, buy 1, buy 1, buy 1. We're going to replicate this experiment again next year because all the girls are past laying age now, so we have to buy 4 more, which is going to be awesome to bring it back in again. Cool? Super fun. Super fun. Okay, let's make it more interesting. Let's purchase now the second, and we call the second. That's Nancy. Now we'll get Nancy. One of the best, Orpington, one of the best layers you can get in Central Oregon. At least from our anecdotal evidence and people that have told me about these things. They lay like fiends. It gets their job, which I guess kind of it is. They're bred to do. They're mostly air. So cute. Same thing. Number of girls. That's what I want to know. I want to know how many eggs I can expect. But you guys answered that question already in take-home exam number 1. So, if I buy 2 birds, I should probably label this, right? Flock number 2. 2 birds. Good. The values of the random variable?
0, 1, 2.
Good. If I buy 2 birds, that's how many girls I could have. That's how many girls I could have. Could have all, could have none, could have one of each. And I think we built this whole distribution, yes?
Yeah.
Do you guys remember which one you grabbed first?
2.
It was 2, both birds. Good. What is the chance of getting both birds to be girls?
0.81.
Love it. Do you remember why? It's 0.9 squared.
It's a vent to the n if number is the amount of times that you choose.
That makes me so happy. Do we feel okay? Well, I'll reiterate that. She's quoting her second project. Thank you, Christine. It's perfect. Are we okay calling it 0.9 both times? Even though it technically isn't? Say yes.
Yeah.
Yes.
Why? Why are we okay?
With replacement.
We're treating it with replacement, but Max is not replacing these birds, right? When he goes into the bin, he's not putting them back. We're taking them home, yeah? But what, Christina, give me, what's this? What's this? Tell me what's on this.
Big number.
Remember what these things look like when you buy them. There are literally hundreds. This is a small bin. This wasn't the bin. I didn't take any pictures that day we got the chicks at the store. I don't know why I didn't, because I'm a dad and I should do that kind of thing. But there were hundreds of birds in those bins, and Max picked 4 of them. So yeah, when he first grabs the first bird, it's 90% of whatever the total is. When he grabs the next bird, assuming he got a girl first, can we assume it's still 90%?
Yes.
Because the population is so huge and the sample drawn is so small. That's the whole point. It's the pumpkins, it's the raid drives, it's that part of that last project again and again and again. Thank you. All right, let's keep going. There we go, Nancy. So, we're okay calling this 0.9 squared? I think it's a great idea. So that becomes 0.81, yeah? Notice, it's now harder to get all girls. Because every time you grab a bird, every time Max grabs a bird out of that bin, it's a coin. He's flipping a coin every single time he grabs a bird. It's not 50-50, it's 90-10. But it's still a coin flip, so there's always that potential of uncertainty that he's going to get a boy. So it went down from 90% to 81%, all girls. Cool! What did you guys do next? I think it was this, yeah?
Yeah.
You went this one and call that 0.1 squared?
Yep. Yeah.
Notice it's also going to get harder to get all boys for the exact same reason. And it's going to get ridiculously unlikely to get all boys. If 90% of them are girls, you shouldn't be grabbing 2 boys if they're indeed all girls. And then it got interesting, didn't it?
Yeah.
Yeah, it did. And just like, yeah, this is the part I didn't like on Wednesday. Now, we know what the answer has to be. 1% and 81% is 82%. So we know it has to be
0.18.
It has to be 18%, yeah, 0.18. But when we tried to do it this way, the numbers weren't jiving, were they?
Right.
Because I think what we did was you said, well, that means you've got to get a girl and a boy.
Right. Plus.
Why was the... Now, hold that thought, Madeline. Give me 30 seconds. We started with this, yes? We said girl and boy. Well, n means multiplied. So we went 0.9 times 0.1. That's 9%. That's shy. Madeline, you're saying add what?
0.01 or 0.1 times 0.9 because you have each possibility of a boy and a girl and a boy and a girl or a girl and a boy.
That's perfect. This is a perfect mathematical representation of the statement I'm about to make, and I think we made it on Wednesday last week. If you want one of the birds to be a girl, that means the other one has to be a boy. Fair enough? Well, if you think about the birds, that means either Bertha is the girl and Nancy is the boy, or
Nancy's the girl.
Nancy's the girl and Bertha's the boy. Now think about the statement I just said. Either Bertha is the girl and Nancy is the boy, Bertha's the boy, and Nancy's the girl. That's a perfect mathematical representation of that idea, yeah? It's beautiful, isn't it? It's beautiful. Now, you can also do it more subtly. Subtly? That's correct. But I like the way that Madeline just read it because we see everything kind of laid out. The trick is when you start having bigger and bigger flocks, that is going to get really, really long. So what a lot of students will do, and this is pretty slick, I think, is they'll say, well, 0.9 times 0.1 is the same as 0.1 times 0.9.
Right.
So what they'll say is that's the same as just 2 times, I'll use, that's fine, 0.9 times 0.1. Now, I like seeing it this way first, personally, because you actually see the entire thing laid out. But then, once we get past it, it gets a little bit cumbersome. And just realize there are 2 ways to have that happen. Nancy's the boy, or Bertha's the boy. Danny, give me that thought. What do you think?
I just know how to deal with more birds.
Good! Thank you, because we're about to get to that. Average. Average number of girls.
1.8.
And this is where the percentage kind of gets in the way. I mean, you have 180% of a girl, but it's like, wait a minute, time out. It's out of 2 birds. So it's easier, I think, average-wise, the average number of girls. Now, how did you get to 1.8, Madeline?
Oh, let me look back here. So,
Multiple different answers.
we have 2 times 0.81,
Check you out.
which is
Component by component, thank you.
2,
1.62
plus 0.18
plus 0.18.
equals 1.8.
Good. That's the component by component wise. My favorite way of doing an average, especially early in the game, because it makes sure you understand what an average is. It's this plus this times this plus this times this plus this times this. It's the way an average is constructed from a weighted mean. Perfect. If you're looking for a shortcut, what can you do? And I have, use your TI, L1, L2, 1 bar stats. I got no problem with you doing that. I've made you suffer through enough of these component by component averages that you've earned the right, obviously, to run a weighted mean in your TI. But on average, you're going to get 1.8 girls per 2 birds. Hopefully that makes sense. In the first flock, when we only bought 1 bird, we picked up 0.9 of a girl. We picked up 2 now. Each time you add a bird to the box, you add 0.9 of a girl again. Now you've got 2 of them. So 2 times 0.9 gives you 1.8. Ha! Fair enough? Hopefully that makes sense. Yeah, pretty straightforward, I think. So every time you add a bird to the box, you're picking up 0.9 more females. 0.9 more females. So you already know what the next average is going to be, don't you?
2.7.
Exactly. For 3 birds, we can start this one kind of in a weird way. X equals number of girls.
It's going to be a table of 9.
Hold that. No. Fighting disaster. So now we're going to build a flock of 3. Renee, answer that question.
I don't.
Oh, you don't have a question. You were just moving. I'm sorry.
Well,
I'm sorry. Apologies. So what I want to do now is I want to have a flock of 3. We're going to add in Marge. Marge the Orpington. She's the oddball of the flock for sure. She doesn't seem to play well with the others as well as the Orpington. The Orpington and the Plymouth Bard, very social. The Delaware is the alpha hen for sure. She's the head of the pecking order. Poor little Marge gets beaten up quite a bit. I've watched this weird behavior with them where I give them 4 equal piles of scratch to pick at for treats. And I'll put 1 in front of each of them. And they'll all start pecking away. And then Mary will go over to Marge's and kick her off of that pile to eat hers. And I pick Marge up and put her on Mary's pile. And Mary goes back and kicks her off again. And I smack Mary in the side of the head. And they keep doing it. I'm like, I can't fight Darwin. I mean, it's just going to happen. So I let it go. So I try to give Marge some love every once in a while. She always finds the best compost, though. Best worms. So she's smarter, weaker, and smaller. Anyway, sorry, dynamics of chicken flocks. Let's buy 3 of them. How many girls can we have?
0, 1, 2, 3.
Go. Beautiful. Now, let's build some probabilities. Now remember, on Wednesday on your exam, I will already have this filled in for you. But this is binomial. We can actually build. We're using this term binomial. We'll come back to it. We're talking about that in a minute. Grab one and build it for me. Which one do you want to build?
3.
3. I think that's the most logical. That's what we're most interested in. What is the chance if I've got that little Happy Meal with 3 little peeps pooping and peeping? What's the chance they're all girls? Go for 0.729. Love it. How'd you get it?
0.9 times
Yes, ma'am. It's 0.9 cubed, isn't it? It's 0.9 cubed. Because every time Max grabs a bird, there's a chance it's a boy. It's a 90% chance it's a girl. There's still a 10% chance it's a boy. And look what just happened again. It's getting harder to get all girls, yes? It's getting harder to get all girls. It went from 90% to 81% to just under 73%. We're dropping. We're dropping exponentially, for that matter. Good. What's the next easiest one to calculate? It's also getting harder to get all boys, yes? It's also getting harder to get all boys. Now, hopefully that makes perfect sense. This is like the chance of all the hard drives at COCC failing. If you compare this to your last project, that's all the hard drives failing, that's all the hard drives working. They're both going down, but that was just going down exponentially even quicker because the base itself is so much smaller. This is also kind of the root of the false positive, false negative question, which you'll see in a couple weeks in your last project. Now it gets interesting. Which one in the middle you want to do? We'll do one? Okay, so if we know we want one girl, what else do we have to accept? We're going to have two boys. So somewhere up here, I know I have to have a 0.9, yeah?
Yep.
What else do I have to have?
Two.
I've got to have two of those, don't I? Now remember the cool way we did this over here, where we had it all listed out, and I got no problem with doing that again. But I'd rather not do that because, and we're going to board really quickly. That's a lame reason. But I think we can logic this out. How many different ways can this occur in a flock of 3 birds? Because that right there is 0.009. It's 0.009. That's too small. Because what I've just done with this statement is I forced one of the birds to be a girl and 2 more to be boys. But I've also picked which bird is a girl in this case. So for example, I'm going to make Bertha be the girl, Marge and Nancy be the boys.
Right, so you have to multiply that by 3.
Why 3?
Because you've got 3 birds and 3 different possibilities.
Let's walk through it. You ready? Either Bertha's the girl, and Marge is a boy, and Nancy's a boy. Or Bertha's a boy, Marge is a girl, Nancy's a boy, or boy, boy, girl. So there's 3 possible ways to assign the girl gender, because there are 3 possible birds. So I vote we slap a 3 in front of that, yeah? Let's put a 3 in front of that, which will take care of all those cases rather than writing them all out. Renee, ask me that question.
Why isn't it 9 different ways?
Why would it be 9? See what how we just kind of spelled it out. We said girl, boy, boy, or boy, girl, boy, or boy, boy, girl. We're out of ways now. Does that make sense?
Yeah, you don't substitute.
We don't have to, because once we've counted them, we don't count them again. I think the 9 is coming from counting them more than one time. So you're double or triple counting. Great point. And sometimes you have to do that, but just not in this particular case, because we're additively, not multiplicatively combining them. That make sense? Good, thank you. So what's that end up being?
0.027.
Yeah, very, very rare. That's still, if you think back to our rules of outliers, that sneaks in under that 5%. Yeah. So you wouldn't expect this to happen if you bought 3 birds. You definitely wouldn't expect that to happen. And you probably wouldn't expect this to happen. It can happen. John, go ahead.
Is it normal if you change a decimal point 2 places, it's your average as well?
The reason it works for this one so beautifully is because of the numbers 0.9 and 0.1. Okay. Unfortunately. I like the connection.
It's not
a generalization. Yeah, we'll come back to that. Hold that thought though, okay? Thank you. Thank you very much for the patterns. Now, check this out. Check this out. We know what the probability of 2 girls is, because that's 0.001, that's 0.027, and this is 0.729. So if you add all that together, we get 73, 75.7. Check my math on this one. Is it 24.3?
Yep.
Did I do that right?
Mm-hmm.
Okay. We know it has to be that. But let's see if we can come at it backwards now. Kind of this way.
Yeah.
We know it's going to have a 0.9 squared, yes?
Yeah.
And it's going to have a 0.1 to the first, because we want 1 boy and 2 girls.
Right.
Now notice what this is if you multiply it all together. It's 0.081. Right? That's 0.81 times 0.1 0.081, which is exactly how many times less than that?
3.
3 times less. Which means the multiplier out front here has to also be 3. Now, don't take my word for it. Look at the birds and figure out why. Look at the birds and assign the genders and figure out why. Look at those birds. Where's the boys and where are the girls? Or where are the girls and where's the boy, I should say. Okay, ready?
3 options.
Boy,
Boy,
girl,
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 girl. There's one way. Ready?
girl, boy, girl.
There's 2.
Girl, girl, boy.
So in other words, there's all 3 ways, yes? The same number of ways as assigning 1 girl as assigning 1 boy. Hopefully that makes sense. The probabilities aren't the same. It's much more likely to have 2 girls and a boy than to have 2 boys and a girl. But the coefficient way of getting them is the same. That's what makes it interesting. Is the average 2.7?
Yeah.
It is, isn't it? John, great question about that, by the way. It's just a function of the numbers we're using, unfortunately. Well, not unfortunately. It's actually just coincidental. So the average number of girls, 2.7 per 3, let's put 2.7, per 3 birds. We added a bird, we added 0.9 more girls to the box. So you already know what the average number is going to be for 4. You already know, don't you? You already know. We'll come back after break and do that, though, because I have to run up to the office real quick. I have a program or 2 or 5 I want to share with you, and I thought I had my little cable with me. I got to run up and get it. So let's take our 5. Let me run back to Grandview, get my little share cable. I'm going to try to grab 2, actually. Does anybody know how to share programs on TIs in this room? Maybe one person. I'll grab 2 and I'll teach somebody how to do it. Let me speed the process up. Okay, so let's take 5 and we'll come back and build my flock, which includes Barry. Cool? Christina, what's up? You look troubled.
Oh, my.